catch my heart, catch my heart, baby.
Time.
Recently, have you been seeing these motion outfit swap videos everywhere? The ones I just showed are all quite eye-catching, right? But they don't require a real person on camera, and you don't need to wait in line for hours on SeeDance. They were generated frame by traditional artisans like me who insist on using local ComfyUI and handcrafting workflows from scratch. In this video, I will teach you step by step how to use loop nodes and ComfyUI, build several universal workflows with you, and truly achieve outfit swap video freedom. First, summarize this type of video. I won't show the source videos due to copyright issues. You can browse short video apps to find them. Here is the direct conclusion. Some have a fixed scene where different characters or the same character in different outfits perform the same actions. Others distribute a continuous set of movements across different characters or looks. Regardless of the type, the implementation shares one characteristic. You need to run the same workflow multiple times with different parameters. I used to write Python scripts for batch processing. But viewers keep asking if it's possible to handle everything purely with nodes and ComfyUI, so you only need to run a workflow. This time, I updated the MieNodes plugin with a new set of loop nodes. Today, I will build a few workflows to demonstrate. Before we start, synchronize our environment and models. Today we mainly use three types of models: image editing, image to video, and control signal-driven video generation. I will use Flux Klein, Wan 2.2, Wan Animate, and LTX 2.3 for the demos, but you can easily swap in your own preferences. For image editing, using Qwen Image Edit 2511 or FireRed Image Edit works perfectly fine too. These models are all mature versions in the current ecosystem. They don't require high ComfyUI versions, and generally no upgrade is needed. The only thing to note is that loop nodes are a new feature of MieNodes. It's best to update it to the latest version through ComfyUI Manager. Start ComfyUI. Begin by building the most basic walking continuous outfit swap workflow. This workflow is actually quite clear. Input the first image, edit the image, generate video from the image, extract the last frame, optionally enhance quality, then use the last frame as a new first image, edit the image, generate video from the image, extract the last frame, optionally enhance quality, then use the last frame as a new first image, edit the image, generate video from the image, and repeat. It's easy to see that the middle section of image editing, image to video, last frame extraction keeps repeating, making it a perfect candidate for a loop. Without further ado, dive right in. First, manually run through one segment to get a feel for the complete pipeline. The goal is to use this image as a starting point, have the character keep walking forward, and switch between different outfits along the way. The first step is image editing. Many models can be used, such as Flux Klein, Qwen Image Edit, and FireRed Image Edit. I browsed through the workflow list and loaded the Flux Klein single image editing workflow. It has low VRAM requirements, runs fast, and the outfit swapping results are quite good. I loaded the FP8 quantized version. Connect the initial image, then pick a vintage preppy prompt from my prompt library, Oxford shirt, knit vest paired with a pleated skirt. The result looks something like this. Don't rush to click run just yet. Continue connecting the video generation pipeline after it. There are many options for simple image to video generation. Since this is an East Asian portrait, I personally think Wan 2.2, which excels at cinematic feel, would be a better fit. Find the Wan 2.2 4-step accelerated image to video workflow in the workflow list. Select all nodes, press Ctrl+C to copy, switch back to the canvas, and Ctrl+V to paste them in. Connect the edited image as the first frame input for image to video. Unify the dimensions to 720 by 1280. Keep the prompt simple. Have the character walk toward the camera with confidence and composure. By the way, a new VBVR LoRa for Wan 2.2 was recently released. It significantly improves motion trajectory coherence and suppresses visual artifacts, so I'll fix the seed first for easier comparison later. Keep other parameters at default and click Run. Note that I'm using the GGUF Q6K quantized model with the light X2V acceleration LoRa. The high noise and low noise samplers each run 2 steps, and generating the entire video takes about 3 minutes. The result is out, and it looks quite good. First, look at the outfit swap effect. Compared to the original image, the clothing replacement is very clean, and the vintage preppy style is faithfully reproduced. The wrinkles on the white Oxford shirt, the texture of the knit vest, and the drape of the black and white plaid pleated skirt all appear very realistic, with natural light and shadow transitions that look like a directly photographed image. Looking at the dynamic video, the overall coherence reaches a very high level. Facial features, hairstyle, clothing details, and background lighting all remain highly consistent throughout the motion. The girl's movement trajectory from adjusting her hair to dropping her hand is smooth and natural, with a strong sense of realism. However, in the latter part of the video, the character walks slightly too fast and lacks composure. Now add the VBVR LoRa and try again. Its full name is quite interesting, very big video reasoning, and it comprehensively enhances video performance. Click Run. It will take a bit more time, and the final generated video looks like this. Comparing the two versions with and without the LoRa, I personally prefer the VBVR result. The character's movement rhythm remains consistent from start to finish. I recommend everyone download and use it. Next is a key step, extract the last frame of the video. Add a Get Image from Batch by Index node, set the index to -1, which means directly grab the last frame. Connect a Save Image node after it, click the Run button above the node, and successfully save the last frame as a separate image. Right-click the image and select Copy to Clipboard, then select the original Load Image node, right-click to paste, and use it as the input image for the second round of image editing. Change the prompt to Bohemian Light Vacation Style. Click Run again, and the second outfit swap video is generated with equally solid quality. All that remains is to use this workflow to sequentially stitch these short video clips together. This is the traditional video continuation workflow. It's indeed a bit tedious to operate, with manual intervention required at every step. If you really want to run an extra long video overnight, relying on repeatedly copying and pasting is simply impractical. This is where loop nodes come in, letting the workflow run itself. How do loops work in ComfyUI? Don't overthink it. A loop node essentially defines an auto-executing sub-process within a workflow. You just tell it what input data to loop through, and the system automatically splits the data into individual pieces and feeds them in one by one. After finishing one, it automatically moves to the next, with no manual intervention needed at all. Next, I will quickly go through the new loop nodes added to MieNodes. This part is more about underlying logic. Just get familiar with them and roughly understand what each one does. The core consists of 4 boundary nodes: loop start, body in, body out, and loop end. In the workflow, they are connected by a continuous line called loop SeeDance, which handles control signals and lifecycle management. Inside the loop body, we primarily use 3 types of auxiliary nodes. The first type is parameter nodes, which retrieve the current loop iteration's input value. They support integers, floats, strings, booleans, and can also directly retrieve the current loop index. The second type is state nodes, specifically designed for passing data between iterations. In addition to basic types, they also support passing images. For example, the last frame from the previous iteration can be stored through state and seamlessly passed to the next iteration. Finally, there are collect and finalize nodes. Collect temporarily packages the results from each loop iteration, and finalize combines these data packages into a final list or file after the loop completes entirely. Hearing just the concepts might feel a bit abstract. Run a simple example to practice. Suppose we want to loop through the 3 numbers 1, 2, and 3. In the loop start node, select int list and enter these 3 values. Inside the loop body, add a get integer parameter node to read the current iteration's number. For easy visualization, I connected a show anything node to simulate data processing, feeding each iteration's result into the collect node and aggregating with finalize after the loop ends. Note the wiring rules here. The collect node must be placed between the body in and body out nodes, indicating I am collecting data inside the loop. The finalize node should be connected after the loop end node, indicating the loop has finished running. Now I take out everything that was collected and combine it. Click Run. Looking at the output, it perfectly prints 1, 2, 3. Besides directly listing numbers, we more commonly use the range mode. Switch the loop start node to range, set start to 1, end to 3, and step to 1. This is standard range syntax, left closed and right open, including the start but not the end. Click Run again and the output is 1, 2. In practical scenarios, looping through numbers is mostly used to execute different parameters. To run different prompts in one click, you need to use a string list. Switch the type. Click Run. Oh no, why is the output all 0, 0, 0? Don't panic. This is a common pitfall. Because we're still using a getInteger parameter node inside the loop body, which defaults to reading the integer type. The loop is passing in strings, and the node type doesn't match, so it returns 0 by default. Switch to the getStringParameter node and run again. The results are immediately correct. The concepts from earlier might still feel a bit abstract. Practice using loops in the Z-Image Turbo image generation workflow first. Load the workflow. In newer versions, if a model is missing, ComfyUI will turn the nodes red even if they are disabled. Clean those up. Now add the loop nodes. First add all 4 core nodes. Select string list and loop through 3 image generation prompts. Use the getStringParameter node to retrieve each iteration's prompt and connect it directly to the positive prompt node. For easier viewing, add an ImageCollect node to gather each iteration's generated image, and finally use the Finalize node to save them all at once. This actually works already, but I want to introduce anchors along the way. An anchor's purpose is to pass data transparently into the loop body. Specifically, when a node inside the loop body connects to an anchor output, each iteration traces back to the original data source directly, rather than repeatedly loading or cloning data inside the loop. The wiring is simple. Connect the external output to a reroute, then to the body in node's anchor input, and connect the anchor output to a reroute. However, in most cases, because of ComfyUI's caching mechanism, external data won't be re-executed by default, so the practical difference is minimal. Click Run. Quickly, we get 3 images, perfectly matching the 3 input prompts, but note that the Save Image node included in the original workflow is outside the loop, so it only saves the initial one. If you want to save inside the loop, you can switch to a Save Image node with output, and then use a collectFiefSmame type approach to bring it into the loop. In the image generation workflow just now, each loop iteration essentially ran independently. You only needed to run different prompts in sequence with no interdependence. But in many advanced workflows, the next iteration must depend on the previous iteration's results. Continue reusing the workflow that demonstrated loop nodes earlier. Remove the string-related nodes and build a more practical number accumulation loop. The core idea in one sentence: use a state node to maintain a running total inside the loop. Initialize it to 0. Each iteration, add the current loop parameter to this total, then write the new result back to state for the next iteration to use. How to wire it specifically. Inside the loop body, first add a getStateInteger node to retrieve the previous iteration's accumulated value. Then use a math operation node to add the current iteration's parameter, such as 1, 2, 3, to this state value. After calculating, write the result back through a setStateInteger node. One critical thing to note: the key names for both the get and set nodes must match exactly. Otherwise, the data won't align and the state won't propagate. To clearly see the changes in each iteration, I continue using showAnything to collect each iteration's accumulated result. A reminder: all state read, write, and collect nodes that should take effect inside the loop must be strictly placed between body in and body out, and the data pipeline must be fully connected into the loop's context line. Otherwise, ComfyUI will skip them entirely. Click Run. Look at the output: 1, 3, 6. First iteration 0 plus 1 equals 1, second iteration 1 plus 2 equals 3, third iteration 3 plus 3 equals 6. Cross-iteration data relay achieved perfectly. Now that we've mastered state passing, return to the original image editing plus image to video workflow and put loop nodes to real use. The core logic this time: each loop iteration takes a new prompt as input. The first iteration uses our prepared initial image directly. From the second iteration onward, it automatically extracts the last frame of the previous video segment, sets it as an image state for the next iteration, and uses it as the new base image for editing. Then it runs image editing and image to video generation, stores the new last frame back into state, and continues the relay. Start building. Add a loop start node, switch to string list, and enter 3 different outfit swap prompts. Add a body in node. Inside the loop body, use a getStringParameter node to retrieve the current prompt and connect it directly to the image editing module's positive prompt. Here comes the key step. Where does the input image for image editing come from? Inside the loop body, add a getStateImage node, pass through the first image to initialize this state, and use its output as the starting point for the image editing pipeline. At the same time, after the image-to-video output produces a last frame, connect a setStateImage node to write the newly generated last frame into state. This way, when the next loop iteration starts, it can automatically read this image. We also need a collectLoopImages node to save each iteration's image to video frames, and after the loop end, use Finalize to merge and save them as a new video. Everything is ready. Click Run. Oops, I need to change the first frame image. This one was pasted from the manual workflow earlier. It's an already edited result. Cancel the task, switch to the original portrait image and run again. Once the progress bar completes, check the result directly. The girl is wearing 3 different outfits, walking toward the camera step by step, with smooth outfit transitions. The tedious process that previously required manually copying, pasting, changing prompts, and clicking run is now fully automated, perfectly achieving the one-click video generation goal we set at the beginning. Theoretically, with this last frame relay approach, we could loop forever and generate infinitely long videos, but when running long workflows in practice, repeatedly using last frames for image to video has 3 obvious problems. First is quality degradation. The output quality of image to video heavily depends on the first frame's clarity, but when continuously using newly generated last frames as the next iteration's first frame, details are lost like making a copy of a copy, and the quality definitely can't match the original image. To mitigate this, you typically need to add a quality enhancement or repainting pipeline after extracting the last frame. Second is consistency drift. Newly generated last frames will most likely be missing some key details from the original image. For example, if the character happens to turn their head in the last frame, the face gets occluded. The next iteration's model can't capture a complete reference and may randomly generate new facial features. The best solution here is to add reference image control or use a character or outfit LoRa to forcibly lock in features. Third is motion continuity, discontinuity. In the videos we just made, each segment had the character walking forward. But at the moment of segment transitions, you can clearly feel the motion pause. The character has to gather momentum again before starting. This is because each video segment is calculated independently, lacking cross-segment motion memory. For ultra-long continuous motions, it's better to generate independent micro-movements for each segment or use pose-controlled video to drive the entire sequence. Since this approach has these limitations, consider a different angle. Are there scenarios where these problems don't matter at all? Yes, such as the recently viral fan outfit swap videos. They perfectly avoid all these pitfalls. The effect of these videos is as follows. The upper layer shows rotating fan blades, and the lower layer shows a girl constantly switching outfits and poses. Visually striking, but the underlying logic is actually quite simple. To recreate it, the first step is getting a fan video. I thought there would be templates in video editing software, but surprisingly couldn't find any. As a traditional artisan, just handcraft one. First, prepare a clean white background fan image. I generated mine through Z-Image Turbo. Drop it into the LTX 2.3 two-stage image-to-video workflow. I used the newly released LTX 2.3 distilled model version 1.1, which the developers say has improvements across many areas. I recommend everyone update to it. I also loaded the VBVR LoRa mentioned earlier to enhance the effect. Generate a 10-second 720 by Noel's Nude 8.0 video with the prompt fan rotating clockwise at a steady speed. Click Run, and the result was ready in just 4 minutes. But this video has a background and can't be directly overlaid. We only need the fan in the middle. How to do it? Those familiar with Wan Animate might think of Segment Anything, which can precisely track specific objects in a video through labeling. However, our fan's background is extremely clean. Using Segment Anything is a bit overkill. There are many simpler methods. One approach is using Segment Anything Ultra from the Layer Mask plugin. Enter wooden fan as the prompt, run it, and save the resulting mask as an image, or use the simpler remove background node, which also requires saving the image. To save time, I'm only running 30 frames for this demo. Click Run, and we get a bunch of black background white fan sequence frames from both approaches. Looking closely at approach 1, there's a frame in the middle where Sam failed. We can retry or replace it with the corresponding frame from the other approach. After fixing the flaws, connect a video merge node at the end to stitch all the processed fan frames back into a looping video, with the fan material sorted. The next step is preparing the character outfit swap video. I loaded a composite workflow. The first half is Flux Klein's single image editing, and the second half is all the nodes copied from the LTX 2.3 image to video workflow. Now, connect these two parts and integrate the loop. First, create a new loop start node, switch the mode to string list, and directly enter 5 different outfit swap prompts. Add a body in node to define the loop range. Inside the loop body, use a getString parameter node to retrieve the current prompt and feed it into the image editing's positive prompt. The edited image should be directly used as the first frame input for the image to video pipeline. For a smooth demo, I'm only running 49 frames per video, which is about 2 seconds. For the image to video prompt here, I suggest keeping it conservative, something like the person lies quietly on the bed, with minimal movement and tiny amplitude. This perfectly accommodates the different outfits generated by the outfit swaps. Finally, add an image collect node to gather each iteration's video frames, then add loop end, image merge, and video merge nodes to stitch the final 5 segments into a 10-second video. Click Run. After about 8 minutes, all 5 rounds of outfit swap videos completed in one go. Check the result. 5 different outfits. The character's expression is natural. Movements are smooth and gentle, fully meeting the standard for fan outfit swap main video. Now only the final step remains. Overlay the fan on top. Create a new workflow with 3 video load nodes, reading in the fan video, the fan mask video, and the character outfit swap video we just generated. Use the image composite mask node. The logic is simple. The character video serves as the base image, the fan video as the foreground, and the mask video controls the transparent areas. After wiring, click Run, and the system will automatically extract the fan based on the mask and overlay it on top of the character. Check the final result. Doesn't it look similar to what you see on short video apps? Now for something even more interesting. Combine motion transfer with character outfit swapping to easily create dance outfit swap videos. Load the Wan Animate motion transfer workflow. In my current testing, it remains the ceiling of motion following solutions. My motion reference video is 721x8 stare at 30 FPS, totaling 383 frames, about 13 seconds. The goal is to input 5 character images in different outfits, each covering 77 frames, relaying in sequence to approximately cover the entire reference video. We covered the original workflow in detail in a previous video. Jump straight into adding loop-related nodes. Create a new loop start node with the mode set to range. Start 0, end 5, step 1. Following the left closed right open rule, this generates exactly the 5 index values 0, 1, 2, 3, 4. Add body in and get integer parameter nodes. In this loop, besides the reference image, the only thing we need to dynamically change is the skip frames parameter for the reference video. It should equal the total number of frames already processed in all previous iterations. Since each segment is fixed at 77 frames, we don't need the numerical state accumulation approach discussed earlier. Direct math is simpler. Current loop integer, that is 0, 1, 2, multiplied by 77. Add a math operation node. Connect A to the current loop parameter and B to the frames per iteration. After calculating, pass the result directly to the video load node skip frames parameter. This way, the first iteration starts from frame 0, the second from frame 77, perfectly staggered. Note that this reference video has audio, so we need 2 collect nodes, one to extract audio from the video load node, and another connected to the final VAE decode output to collect video frames. After the loop finishes, merge and output them separately. Next, handle the reference images. You can batch import from a folder or like me, use 5 separate image load nodes to upload the same character in 5 different outfits. Then use image batch multi from KJ-nodes to pack them into a single image batch. Inside the loop body, add a getImage from batch node and use the loop index to extract them in sequence. Some might ask, can't we just use the loop's integer parameter directly as the image index? Indeed, right now they're both 0 through 4, but if you change the loop range later, independently managing the image batch prevents the entire workflow from erroring out, which is better for extensibility. Click Run. Wan Animate is a bit slower. It took about 25 minutes in total. Check the result. Characters in different outfits hit their marks precisely, completely replicating the reference video's motion trajectory. The outfit transitions are smooth and natural, with no sense of incongruity. If you want more precisely timed transitions, switch the loop mode to int list and manually specify which frame to perform the outfit switch, giving you precise control over the rhythm. You can also switch the video pipeline from image to video to first and last frame image generation, which can produce smoother deformations and transition effects. That wraps up the demo portion. To summarize, current open-source AI image and video models are already very capable of generating outfit swap videos. Whether it's image editing or image-to-video generation, the output quality is high, reference effects are strong, and motion replication is stable. Issues like limited single video duration and consistency drift can all be addressed through the loop nodes plus multi-segment merging approach. This not only breaks through duration limits but also compresses what originally required manually repeating a dozen steps into a single one-click run, maximizing efficiency. I hope today's video gives you the confidence to say, when you come across interesting motion outfit swap videos, I can recreate this. Alright, that's it for today's video. If you found this content helpful, please give it a like to show your support. All models, plugins, and workflow links mentioned in the video are in the description. Feel free to grab what you need. See you in the next video.